I feel like is the echo any better now?
Yeah, I think so. Karen, say something again.
Test, test.
Yeah.
Okay.
Okay, Shibu, Mateo, whenever you're ready, you can go ahead and share your screen.
All right, let me start sharing my screen. See the slides?
Yes, we can see them.
Shibu, can you try to speak and see if we can hear you?
Yes. Can you hear me?
Yes, we can. Christine, would you give us a go once it's the right time to start?
All right, yep, you can go right ahead.
Great. All right. Well, thank you everyone for joining. And thanks to Linaro for hosting this remote session despite the situation. I'm Matteo Carlini. I'm the Director of Software Technology Management at ARM in the Open Source Software Group.
Hi, I'm Shibu Kriakos. I am also one of the technology managers in the Open Source Software Group.
But today we are here to represent the trustedfirma.org Open Governance Community Project. So bear with us for the next 25 minutes. We are going to give you a few updates and all the exciting news around the project. And trust us, there are a lot of good news. So let's start with a slide full of headlines. So these are all headlines which made the news in the past couple of years regarding security vulnerabilities. You might recognize some of them in the middle, very popular ones. But the key point I would like to make is that there are all sorts of vulnerabilities across all the possible devices which we interact with every day in our life. There are IoT devices, cameras, smartphones, cloud services, as well as cars, can be autonomous cars and also the traditional manual cars. So this is a very generic slide, but if we go a bit more in deep and we see the firmware vulnerabilities that are extracted from the NIST vulnerability database, you can see that firmware is increasingly becoming the preferred target for all the attacks across all the systems. So this is a picture over the last 20 years, and you will see the increase. So why that? So there are many reasons for this increase. One could think about operating system kernels, applications that are getting more robust, connectivity protocols that are implementing new features and new handshake mechanisms. So the attackers are trying to target lower in the stack, and they are reaching out to the firmware. But the other important reason, the key reason for me, is that the firmware is the highest privileged piece of software in all our devices. Higher privilege than any kernel, than any hypervisor. So effectively, if you own the firmware on a device, you own the device. But don't be afraid, don't be scared, there is hope. There is always hope. And we strongly believe that the hope must be built on top of collaboration. Sure, if I can move this, right. Collaboration. Collaboration because security challenges are complex. Think about Spectre. So how long would it take to properly understand what the Spectre attack is really about? And how long did it take to the industry to react to Spectre and find the proper security workarounds for the Spectre attacks? But it's also a security by scale problem. So if you look at the right side of the picture, these are all the industry vendors from the IoT market in 2019. So it's really an economy by scale exercise. We need to develop security fixes that can be deployed and applied across the whole ecosystem. And this can only be done, from our point of view, through through collaboration. because collaboration is the key to solve the complexity of the security problems and really to create one solution in one single place that solves the security challenges once and for all the ecosystem. And that's the main reason why we created Trusted Firmware as a platform, as a community platform to build security in a collaborative way. So Trusted Firmware is an open governance community project which provides a reference implementation, all open source, of the secure world software for ARM processors and ARM-based platforms across all the market segments. It's open governance in the sense that its membership is open to all, and the governance is transparent and is overseen by two main bodies. On the left side, you will see the board of directors from the project members, which decides on the strategic direction and financial direction of the project. And on the right side, you see the technical steering committee, which decides on the technical direction. So how is the collaboration going? Because we talk about collaboration. Well, I would say it's going pretty well. So this is a visual representation of the external contributions that we see coming into the project from the ecosystem. So this is a count of the contributions that are not from ARM, but are from the ecosystem over time since the beginning of the project. So we take as a starting point 2013, when ARM Trusted Firmware was launched. Now it's not called ARM Trusted Firmware anymore. Now it's called Trusted Firmware A, or TFA for friends, for the application processor. Initially, clearly, the contribution were set to 0 when we started. And then slowly over time, contributions started to increase. In 2016, the first improvement, we removed all the legal paperwork and the need for having a signed CLA in place for being able to contribute. So since then, since 2016, we accept all contributions under the terms of DCO, and the license has always been a permissive BSD free close license. And then continuous improvement up until 2 years ago, 2018, with the launch of Trusted Firmware M for all the microcontroller space. A few months later, in the autumn of 2018, with 6 founding members, we launched the TrustedFirmware.org community project. And the increase of collaboration continued up until last September 2019 in San Diego, sunny San Diego. Back at the time, we were all available to travel. So we announced that OPT was also joining Trusted Firmware to continue the collaboration and to enlarge the family of projects which are part of TrustedFirmware.org. So in terms of contributions, only taking into account the last couple of years, there has been an increase of more than 120% of contributions, with peaks that reaches half of the contributions coming from external partners versus ARM in specific time periods. So it's really going well. It's really a success story about collaboration. But we're not stopping here. The family is expanding, the family of projects being part of TrustedFirmware.org. So we are very, very pleased to announce today that Hafnium is joining the Trusted Firmware project. So now, what is Hafnium? Hafnium is a project that was originally started by Google, by the Google Android security team. ARM and Google have been collaborating around Hafnium for the past couple of years. Hafnium comes into Trusted Firmware as a reference secure partition manager for the systems which implements the ARM 8.4 Securial 2 virtualization extension. And that's on the application processor. I'm talking about the application processor side. Hafnium comes with a minimal code base, so with very reduced attack surface. It enforces the principle of least privilege, and it adds an extra layer to the defense in-depth concepts on our trust zone software space. And in terms of use cases, it enables the isolation of one of multiple trusted execution instances running behind trust zone. So if we look at the picture, so here on the left side, it's a traditional system which are not Secure-EL2 enabled. So these are not 8.4 systems. And we are transitioning towards system like this, in which above trusted firmware A, there is Hafnium SPM, which allows multiple trusted execution environments. There is a link to the initial code base into tf.org. And the other good news is that Hafnium is joining with the same licensing scheme as the rest of the trusted firmware project. So a permissive BSD license. So let's have a final look, a deeper look at the software architecture that we are now building then on the application processor side, on the A-class processors. So on the picture, you will see all the blue boxes will be provided as a reference, open source, from the trustedfirmware.org project. So starting from the EL3 runtime firmware, which is the traditional trusted firmware A, going above Hafnium SPM running at SEL2, and on top, we provide the reference given by OPT as a trusted OS with its own trusted applications on top, which might also implement PSA secure services. And then partners and ecosystem can implement their own specific trusted OSs, their own specific platform services, which are all isolated one another thanks to the virtualization extension. So we are really achieving isolation through virtualization in the secure world. And the other point I would like to stress is that trusted firmware, all these components will implement all the standard interfaces which are defined by the ARM PSA firmware framework for the A-class, which is most friendly known as the SPCI interface. This is really key because we strongly believe that the key for a smooth transition into a more secure firmware space goes through the standardization of the interfaces between the normal world and the secure world. So we strongly encourage our partners to adopt the standard interfaces defined in the ARM PSA framework. With all of that, we will be able to achieve defragmentation of the secure firmware space, both at EL3 and at SEL2. And what we gain out of that is the integration for our partners, the testing processes, to provide a way for updating the firmware in a standard way, which again is useful to fix the firmware vulnerabilities in field. And we ease the process of auditing and security assessment of devices. So eventually, I move this thing around again, we increase the security of our devices and we achieve firmware transparency, ultimately reducing the time to market and the development cost for the entire ecosystem. And with that, I'm passing over to Shabu for the continuation.
Hi, everyone. Hope you can see my screen now.
Not yet? Now we can.
Hi, everyone. I would like to get started by briefly mentioning about Trusted Firmware M, which is one of the projects in the trustedfirmware.org project portfolio. Trusted Firmware M provides a secure processing environment for Cortex-M devices that today powers millions of IoT endpoints and embedded applications. It is a reference implementation of the platform security architecture, and it provides a secure boot that authenticates the runtime images, and it provides a standard set of runtime secure services such as storage, crypto, and attestation that is made available through these standard PSA APIs. The TFM project has been launched for the last 2 years, and in the last 2 years, it has come a long way. For example, it has provided as the root of trust for a long list of silicon platforms and RTOSes to be PSA certified under the PSA certification program. The project started off by supporting a bunch of ARM reference platforms, and now the supported platforms are in the increase, starting off with the Cypress PSOC 64, which is now supported upstream in TFM, and there is active work going on to upstream more V8M platforms such as the NXP LPC55 and ST's STM32L5. The project is also starting to integrate with a lot of open source RTOSes. So early on in 2019, we started off with integrating with EmbedOS, followed by Sapphire. And later on in 2019, we started integrating with the Amazon FreeRTOS and RT-Thread. And the aim by providing such an ecosystem of TFM on different silicons and on operating systems is to provide IoT application developers to avail security services from Trusted Firmware M, thereby making IoT endpoints more secure. And I'm glad to say during this month, the project is achieving a great milestone by providing the TFM 1.0 release tag. So this is a culmination of the work from the TFM ecosystem over the last 2 years to implement and align to almost all the PSA specifications, mostly around 1.0, meeting all the PSA certification requirement, and thereby being the root of trust for a large variety of Cortex-M devices. And I would say this is just the beginning, and there is still an exciting roadmap ahead for this project. For example, providing different TFM profiles for different memory configurations, supporting a lot of V8M platforms, etc., etc. So I would say watch the space. Now we have briefly looked at a few trusted firmware projects that ensure security in end devices. But nowadays, most of these devices also needs to establish secure links to say connect to cloud or any other end applications. MBTLS has been an extensively used TLS library to provide secure, authenticated, and encrypted connection over unreliable networks. What the TLS library basically does is abstracts away all the cryptographic certification management and authentication complexity that's associated with the TLS protocol away from the application. And so far, the MBTLS project was available under the ARM GitHub as an open source project. And today, I'm glad to announce that the MBTLS project is transitioning to become a trustedfirmware.org open governance project. And this move is being made with the sole aim to take this project even to be a far well adopted community project where the strategic and technical direction of the project is driven by the trustedfirmware.org members. The project continues to be available under the Apache 2 license. And today, if you go to the trustedfirmware.org website, we have gone live with a new MBTLS mailing list that would be a good starting point for the entire ecosystem to collaborate on future enhancements on the MBTLS project. One of the associated activities that has been happening with within MBTLS over the last several months has been to basically split the MBTLS project into 2 halves. The MBTLS project providing all the TLS network security aspect and the X4 509 management, while the second part of the project called PSA Crypto bringing together all the crypto primitives in the MBTLS library and making it accessible through a set of PSA crypto APIs. This second project has been driven by the Platform Security Architecture program, aiming to provide a crypto library that devices can use for different purposes, such as securing the valuable assets in their system, to establish secure connections, and to securely provide secure updates to the end platforms. For example, usage model on a Cortex-A or Cortex-M devices, as shown on the right-hand side of the screen, would be the PSA crypto library being on the trusted execution environment or the secure world, and applications or embed TLS for that matter can avail cryptographic functionality from the PSA crypto library through a standard set of PSA APIs. In addition to the developer-facing API, the project is also starting to define a set of low-level APIs that would enable the library to interface with a huge array of secure elements and accelerators. I would say the project is still in its infancy. There's a long way to go, but we have in the recent months seen a lot of momentum in silicon vendors trying to adopt this library because it brings standardization around these APIs. So I'd like to request you to have a look into this project under trustedformat.org. Now, very quickly, we have gone through a bunch of projects that trustedformat.org today host. So traditionally, it has been a hosting place for TFA and Opti, which together so far has provided the trusted execution environment for Cortex-A devices. With the advent of Hafnium, it's going to provide a secure hypervisor for future Cortex-A devices. TFM, of course, provides the secure processing environment for Cortex-M devices. The Embed TLS project ensuring you can establish secure connections from these endpoints. PSA Crypto providing a crypto library with some standard PSA Crypto APIs. So we truly believe that trustedformat.org is providing that collaborative platform with a complete and coherent set of open source secure software solutions that can be deployed across the ARM ecosystem. Now that we have looked at the different project that tf.org hosts today, I would like to briefly touch upon how does the project operate. So as Matthew was saying earlier on, it has got a board which sets the strategic direction of the project, and the technical steering committee is responsible for the technical direction of the project, the code base, the maintainership, and the different technical topics. And during 2018 and during 2019, we had all these great members collaborating under the trustedformat.org board and the technical steering committee to lead these different projects in terms of strategic direction and the technical direction. And we have got new members joining the project as well. And today I'm very glad to announce that Renesas and NXP is joining trustedformat.org as its latest platinum members. We are sure that with the huge experience and expertise that Renesas and NXP has over the years in creating ARM-based secure devices, it will be a huge value add for the project for these two companies to work under trustedformat.org to set the future direction of the project. So welcome Renesas and NXP. As we come to the close of this session, I would like to quickly go through what is the collaboration on a day-to-day basis as far as the project goes. So there are, as we talked about during the keynote all along, it's all around open collaboration. So any new idea starts coming up through the mailing list. So each of these projects have got its own mailing list. A lot of people are registered to it, and now it's becoming a very busy place where there are a lot of conversations around new designs and problems that people are facing once they're deploying these projects in end devices. Then we're starting to have bi-weekly open tech forums, which is normally attended by 40 to 50 people for each of these areas, where main technical topics are brought up by key experts, and these are presented, and then follow-up discussions are being held. We are also starting to have an annual workshop for some of the key project areas. So it started off with a TFM workshop back in October in Lyon, which had around 36 people attending a 2-day workshop discussing quite a lot of key TFM technical topics. And we hope once the travel restrictions are lifted, we can have similar workshop for other projects as well in the coming years. So once these design ideas are firmed up, the patches comes in the trustedformat.org get it for open reviews, giving a chance for everyone to have a look at the code and review the code. And once it's all gone through the review cycle, it finally gets hosted in the trustedfirmware.org Git. From there on, it's available through various open source licenses for consumption to end devices. And to complete the cycle, we are also starting to have an open test system, which we call Trusted Firmware OpenCI, which is available in this link, where we are trying to make sure that all the member platforms are always tested and up to the mark with the latest code bases for each of these projects. So by starting with design, which starts out in the open, going through development, reviews, and testing, tf.org provides that complete open collaborative development lifecycle. So as we come to the end of the keynote, I would like to conclude by saying that innovation is exploding in all aspects of our lives, whether it's artificial intelligence, autonomous machines, 5G networks, cloud computing, mobile devices, or even IoT networks. And what I'm showing on the right-hand side is some of the major challenges that has come out in the major cybersecurity reports, showing there are going to be a lot of challenges in the cybersecurity space in the coming decade. But one of the very recurring themes in many of these reports is, of course, the complexity of security is ever in the increase. We are going to see an increasing skills gap in trying to solve some of these challenging security issues. Of course, the vulnerability and attack surface is ever in the increase. And if we combine this data with what Matteo was showing in the beginning of the presentation around the NIST database number, about the number of firmware vulnerabilities that has hit us during 2019, and it hitting a record high during 2019, we think it's quite essential that the ARM ecosystem that is going to create the next billion devices should definitely come together, bringing all their expertise under the trustedfirmware.org umbrella to make even more secure devices during the coming decade. And with that, I would like to conclude the presentation, but just remind everyone to stay safe and secure as we go through some of these challenging times. Please do visit trustedfirmware.org. Please do get yourself registered to all the mailing lists so that you can become part of the collaboration right from design, implementation, and testing. Thank you very much.
Thank you,
Thank you all.
Shivu. Thank you, Matteo.
Hello, can you hear me now? Test, test.
Yes.
All
I
right.
can hear you.
Sounds like you can hear me now. All right, just let me know when you want to get started here. I don't know if we have Stefano online yet or not.
I'll check for him, but you can go ahead and share your slides whenever you're ready.
Okay, are you going to drive the slides or do you want me to go ahead and share my screen?
If you can share your screen, that would be great.
All right. Move this out of the way. All right, can you see that?
Yes.
All right, so we'll get started. First off, good morning and good afternoon. Welcome to Linaro Tech Day session on heterogeneous hardware accelerated OCI containers and secure OCI containers. I am Wes Skeffington and my co-presenter is Stefano Stavellini. We both work within the systems engineering and systems software team at Xilinx. And what we're hoping to talk to you today about is briefly about a concept and collaboration opportunity that we're seeking around extending the OCI framework to bring heterogeneous hardware and VM isolated containers as first-class citizens into the OCI ecosystem. So in that light, the high-level goal that we're working towards, and the reason we're wanting to work with this community, Linaro in general, and a broader set of software and silicon vendors, is to work with the OCI committee and extend these specifications to support the utilization as a framework for more heterogeneous hardware capabilities within the containers ecosystem. And so what do we mean by heterogeneous hardware? First, we're talking about things like accelerators that can be implemented in FPGAs, GPUs, et cetera, and not replacing them, but really tying them into the OCI for deployment and then container access to those accelerator resources. Second is we want to create this, call it a common dashboard or a common plane of glass for managing these heterogeneous platforms. And that includes things like the asymmetric multi-core processing that many of us implement in Cortex-R and Cortex-M coprocessors that sit next to your application processors. And then lastly, overall kernel deployment. We'll talk about this as a thing called RunX, where we're standing up containers as isolated using Xen hypervisor as a reference implementation. And of course, that can be extended to other hypervisors. So what's the overall motivation here? The real motivation here is that recognition that the OCI is quickly growing as an application packaging and deployment framework. And it's not just happening in data centers, it's also happening at edge targets, whether your edge is an on-premise server, or you're talking about the very edge where the digital physical boundary is bridged in microcontroller type devices. Simultaneously, our application performance growth is really ever more dependent on heterogeneous platform targets, whether those be things that we call domain-specific hardware architectures, et cetera. But we have really a big motivation as a broader compute industry and software industry to really bridge this gap between the container software ecosystem and these increasingly domain-specific hardware architectures. So that's really what we're trying to work towards. So first, we're going to talk about linking heterogeneous hardware accelerators and to native Run-C containers. And again, what we're trying to do is do this at a level within the OCI framework that is agnostic to the different orchestration frameworks and other technologies that people have built on top of containers in terms of container management and orchestration. So if we look at just a heterogeneous hardware access at startup, what we're specifically talking first to is an image spec extension to be able to have this additional metadata, key value pairs to identify that there's an incremental resource required for the container, and then where and what is that device data associated with that. So in this example, we've got an FPGA-based accelerator. We would represent that in the image manifest of the container with this device name and then pointing to the associated FPGA bit string that would be programmed. Container D would then know how to unwrap that and work with the device specific configuration triggered based on that resource metadata hook. The device configuration block would then take care of the device specific functionality to get that resource and bit string loaded into the system, and then return that device name and any other associated information to the shim that can be used by run C to actually stand up the container and expose the associated hardware resources that that container is going to access. In terms of how we go do that, we are working, or we've looked at in our existing prototypes, just passing those as extra arguments when we call run C, but a more scalable solution might be in terms of the dynamic definition of the config.json file associated with that container. So again, it's not about replacing Kubernetes or run C or containerd in itself. It's about being able to use those mechanisms as an orchestration framework for tying into these heterogeneous platforms. So then if we flip that and look at the other side of it, as you look at resource management, obviously there's startup and shutdown piece of it, kind of works in the opposite manner, where once we get the stop command for the associated container, we can shut down and stop that container and then bring back that state information to the device configuration. So in this case, or this example of an FPGA-based accelerator, then we can tear down and free up that partial reconfiguration region, say, within the FPGA or what other device that you're talking to. So that's sort of the example of using run C in combination with the heterogeneous accelerator orchestration framework. So with that, then we'll jump into talking about the concept around secure containers with Zen. It looks like Stefano, you're online.
Yeah, I'm in. So, all right, I can take it from here on RunX. So let me add a few words on what RunX is before we draw a parallel to what just Wes described in this world. So RunX is a new OCI compatible container runtime engine and is under LF Edge. So the idea is that it can be used to run containers securely using Zen hypervisor technologies. So what it does is it creates a very small virtual machine, as small as possible, just enough to create an environment to run the container inside. So the benefit is that it's just a very different runtime environment from a normal container runtime like runC. So it has very different properties. For instance, as much stronger real-time separation and isolation and stronger security guarantees. Yeah, so it's a micro VM in the sense that the kernel and RAM disk provided by RunX to run the container inside. And if you look at, there is a color scheme, darker blue is provided by RunX, while lighter blue is the container itself. So is there going to be as small as possible, just a smallest possible environment to run the container? Wes, you can slide. Right, but one of the first thing that we want to do, which I think is very interesting, is to extend the OCI image specification so that we can also describe kernels and RAM disks. So the idea is that a kernel today, container today is basically a user space Linux or in general POSIX set of binaries, but it could be containing kernel space binaries too. So for instance, you can imagine a container rootfs coming with a kernel binary inside. Under /boot or somewhere else, be flagged as a kernel. So there could be a key value pair in the manifest saying, look, this container actually also contains a kernel. And then runx will go look at this manifest, find the key value pair, and then it will actually use the kernel and RAM disk that come with the container to start the VM. So if you think of why will you want to do that, there is actually a very good use case for this. Next slide. Yeah, an RTOS. So you might wanna run an RTOS and deploying it dynamically using runx. So a real-time OS like Zephyr, you can imagine building your application using Zephyr or FreeRTOS, one of those, because you have real-time or determinism RQ latency requirements, and you still want to deploy dynamically, right? You might still want to benefit from the lifecycle management the OCI tools come with, which is very powerful and very convenient to use. So what this allows you is to build your application as an RTOS, as a proper kernel RTOS, and then pushing it to the Docker Hub, and then dynamically deploying it using orchestration framework like Kubernetes, using Containerd, using all your regular OCI tools, and transparently, your RTOS will get run inside the VM, and it will also show up as one of the containers running in your system. Next slide. And this now ties back exactly what Wes described in detail earlier, which is you can still do the same thing with accelerators and hardware assignment to containers that are run with runx. Containers that are run with runx, they could be both of the kind that come with the kernel or of the kind that the kernel is provided by runx. But either way, this accelerator can be still configured correctly by the device configuration component, and then the hardware resources such as MMIO region, RQ, and anything related will be directly assigned to the VM so that the container can have direct access. And with that, I give you the ball back to you.
All right, thanks, Stefano. So again, sticking in this framework of the OCI really being valuable in terms of a management and deployment common pane of glass for a heterogeneous set of platforms. If we look at AMP, or asymmetric multi-core processing, there's an existing solution, at least on target for that, around OpenAMP. And it's a great framework that within Linux makes use of remote proc. And so we thought a logical extension of that, such that that same set of firmware resources could be managed through that common pane of glass for the overall system management, was to extend this same idea of a resource and device data, but tying that in now to, say, RPU or Cortex-M firmware that can be managed through that same device configuration block. So again, what this would look like is from it wouldn't be a traditional Linux container, but really it's just the packaging that goes around it to enable that to be deployed, and then with the on-target Containerd and Containerd shim, pass that information to the device configuration, which then can interact with remote proc and the corresponding slave processor. So again, it's not about replacing OpenAMP, it's about adding a layer on top of OpenAMP to be able to support those Cortex-R and Cortex-M firmwares in a common deployment infrastructure. So to talk to where are we looking for collaboration, why do we want to really engage with the broader audience here, is that really we've seen a lot of vendor-specific implementations around enabling containers and container orchestration for heterogeneous hardware, but they're just that, vendor-specific. And so we want to take a crack at really working with the Open Container Initiative Committee, such that we can get these changes associated with the image specification and the runtime specification upstreamed in a manner that provides a common design pattern for folks to tie their heterogeneous platforms into the OCI deployment infrastructure. So within the OCI image specification, three key things that we are working towards is really definition of the key value pairs for heterogeneous accelerators. So we talked about the resource, device data, kernel, RAM disk, as just initial examples of what the key value pairs that we're trying to work towards. Also talking about where does one locate the device-specific configuration data packaging within the container image. In our existing prototypes, we are just, we've picked a definition of this, but where we need feedback and collaborations, does that work for everybody? On the runtime specification in our prototyping efforts, we found that container D often does some filtering or removal of relevant image spec data that we really think is required for device configuration. And so making sure that we get a standard definition in terms of how container D treats some of these additional key value pairs that we want added in the image spec. We also need to standardize the way the container device configuration data is really passed between the container and the host. In our early prototypes, we were using some of the environmental variables passing. I think that's going to be a little bit brittle, and this is again, whereas we look to what's the right long-term solution so that we can do this in a standardized design pattern. And lastly is being able to standardize the method by which we export those dynamic hardware devices to the actual container itself. So these are sort of 6 top-level things that we're really looking for collaboration within Linaro and other contributors to upstream within the OCI specifications. So just in summary, Xilinx right now really has a small development team that's working on prototyping this. Of course, we're doing that within the context of FPGA SoCs. And we really are looking for additional inputs so we don't have a overly vendor siloed view of what different platforms need from configuration data and the way that needs to be passed. And then ultimately really looking for a multi-customer, multi-vendor drive to getting the OCI committee to support the specification changes that we're advocating for. As Stefano mentioned, we already have some collaborations underway with Project Eve within the Linux Foundation Edge organization. You can go to that wiki and kind of see where things are in terms of that progress around the RunX efforts. And really our key message here is this is an early proposal. We're working early prototypes within our team. And really what we're asking for is other contributors here that would see benefit or help here for managing these heterogeneous accelerators, asymmetric multi-core systems, et cetera. And again, the key value here is really about an integrated standards-based solution for the infrastructure that can be used in a way that is not vendor specific. So if you're interested in participating, giving some input and helping steer some of the early prototyping work that our team is doing, please reach out to myself and Stefano. And with that, I think we've wrapped up 5 minutes for Q&A if there is any.
Yeah, if anyone has any questions, please just type them into the chat. Or those on YouTube, just type that into the YouTube chat and I'll bring it here. I guess you guys did a good job covering everything then.
All right, well, thank you for the opportunity to present and share with the team. Again, I think this is an important subject, so please reach out to us if you are interested, and we'll look forward to the next, hopefully in-person Linaro Connect to give an update.
Yes, thank you both. And we'll be sharing the slides as well as a recording in the next few days. Thanks, everyone.
Goodbye.
Hey, Christine.
Hey, Matteo.
Should I give it a go?
Yes, you're all set. Take it away.
Can you see my screen?
Yes, we can see it.
Great. All right. Thanks everyone for joining. That's again Matteo Carlini, Director of Software Technology Management at ARM in the Open Source Software Group. So this talk is specifically on the ARM64 Linux kernel architectural updates. So the ARM64 kernel team at ARM does a lot of things. So and this talk will not cover everything. This is specifically on the architectural enablement that we do, which is the majority of the work that we do as ARM64 kernel maintainers. So just let me start with a few pointers. There is a public table available on developer.arm.com, which precisely maps all the specific architectural features from the ARM 8.1 architecture up to 8.6, and the specific kernel revision in which that feature got enabled for the first time. And there are also some notes for the ongoing features or features that are at the moment queued or under development. So go check it out because it has a lot of good information in it. So the introduction that I would like to make is a high-level view on the status of the architectural enablement that we do in the kernel against the ARM architecture from 8.0 up to 8.6 and new features. So this slide is not intended to dig into each one of the specific architectural features. You can go have a look at the table offline. This is just to give you an overview on roughly where we are. So you can see that 8.0 was the beginning of the ARM64 kernel, so everything clear in there. Then going clockwise, top left, 8.1, again, everything done, nothing left to be done. With 8.2, there are bits and pieces left over, which I will cover in a minute. But broadly, the architecture is completed, and the support in the kernel is also completed. The big mixing item from the 8.3 and the 8.4 architecture is probably the nested virtualization extension, the NV, which you will see in light orange. And that is under development. I'll explain the status later on. But other than that, 8.3 is practically complete. I will share some updates on the pointer authentication feature. And from the 8.4, we have MPAM, which actually is not listed here because it's a separate spec. But I'll talk about MPAM a bit, and I'll talk about the remaining status of nested virtualization. Bottom left, 8.5, you can see we are halfway through the enablement. The great focus is around completing the development of memory tagging and BTI, branch target identification, which are the main security features that got enabled with the 8.5 extension. A few other features have been enabled already, speculation barriers, the random number generator, and a few other stuff, which I will mention later on. From the 8.6 architecture, we are, let's say, at the beginning of the enablement. 8.6 was announced last September, 6 months ago. So we enabled the bits and pieces through hardware cap exposed to user space. And then we are working on the rest on the enablement in a priority order, which I will talk about later. New features, so these are the so-called new architectural features, which are currently not part of the traditional naming scheme of the ARM architecture. So SV2, transactional memory, and then I'll talk just a little bit about Morello. There's been a talk yesterday from a colleague of mine about Morello, and I'll just grab some highlights on that talk to recap the current situation. So moving on into the 8.2, as I said, almost completed. There are few leftovers. One is the statistical profiling extensions needs to be exposed into KVM guests. There is a prototype code available on a developer's branch. Now the activity is going to be picked up by the KVM ARM64 community and should be reposted soon on list. And that will complete the SPE enablement. Other than, at the bottom, the last bullet point, other than some perf tool improvements, which again are being developed as we speak on the list. And this is going to add support for SPE band in perf, so that from user space you can exercise and use the statistical counters. And the second bullet point, RAS. So we completed the support for the architectural firmware first RAS approach since 4.16, actually a year ago, roughly, with few additions that got added into 5.0, like wiring up SDI into the API table. What is left to be done is the so-called kernel first RAS approach, which is ongoing by the community. So ARM is going to produce a specification which defines the ARM error source table. Specification is in beta at the moment, available on developer, and is going to be EAC pretty soon in April. That completes the 8.2 enablement. If we move forward, so I spoke about pointer authentication. It's an 8.3 extension with an additional bit of the architecture, bit not strictly speaking, an additional feature of the architecture in 8.6. The 8.3 extension is practically complete. You will see the step-by-step enablement in the specific kernel versions listed here. So in 5.0, we enabled the user space support. We added ptrace reg sets for key management in 5.1, KVM support added in 5.2, and now pretty recently, a few days ago, the ARM64 maintainers queued the in-kernel support for function return address protection. Now, clearly, this is upon any regression or any fix that we might encounter during the merge window, which will open pretty soon as 5.6 is tagged and released. We're still working on a crash utility for crash dump analysis, which is ongoing. And as I said, the 8.6 architecture also foresees some improvements, some enhancements on pointer authentication, which are currently in discussion on list. So it's mainly two topics, some enhanced pointer row generation algorithm, and then some faults that get generated when the authenticate instruction fails. So next topic is around nested virtualization. So nested virtualization is a huge beast. It comes together with both the 8.3 and the 8.4 extensions, so such as a unique patch set, which enables the features altogether. It's huge. There are around 100 patches, little less than 100 patches on list to review. The development is carried over by the KVM ARM64 community. The ARM-specific kernel team is reviewing and is testing all the features with the internal FPGA that we have available, which implements the feature. Partners are very welcome to test the feature on their silicon, to provide feedbacks, to provide hacks on the patch sets on list. The current patch sets also include two features which comes from the 8.4 and 8.5 architecture. You will see listed there. The translation table label, which reduce the cost of TLB invalidation, and the GTG, gas translation granule size. Chances are that these two features will be descoped from the huge patch set above so that they can progress quite quickly with respect to a nested build that will take some time. It will take some iterations because before it settles down and before it's in a state it can be merged. Moving on, HEMPAM, so memory partitioning and monitoring. So you might know, but if you don't know, we are working to extend an existing interface, which is based on an Intel framework, which is called resource control, RES control. It's based on an Intel RDT feature. And this is for consistency. because we want the ARM feature to work seamlessly with our partners using the same user space interface. But this also means that we have to put a lot of effort, which we already did, and we keep putting a lot of effort in reworking the interface, which was not multi-architecture ready. So the first step that we are taking is reworking, fixing, extending that interface to make it multi-architecture. And this effort resulted in another huge patch set, more than 130 patches, which are currently available in a developers branch, again, for validation and testing. But bear in mind the rework, just the rework of the REST control interface to make it multi-architecture will progress throughout all 2020. And in terms of the specific ARM64 architectural bits, architectural enablement of the feature, we are really targeting now 2021, because this needs to happen after we make the interface multi-architecture. The table below tries to summarize which are the MPAM controls and how do they map with the REST control interface. So you will see that there are two main categories of controls which can be driven by the REST control interface. One is the cache portion bitmaps for level 2 and level 3 caches. And the other one is the memory bandwidth portion bitmap. So these can be and will be controlled by the existing resource control interface. The other features which comes with the ARM MPAM architecture are not so easily driven by the REST control interface. Actually, there is no way at the moment to drive those controls. So this has to be a separate conversation once we finalize the 2.1 involves for systems that have the need to drive those MPAM controls. Moving on again, 8.5, branch target identification. So if the pointer authentication feature protects against return-oriented programming, branch target identification protects against jump-oriented programming. So there are two security features that comes very much, well, the idea is to deploy them very much together to protect against these sort of attacks. What is the state of the enablement of BTI? So the user space support has been queued just recently, again, a few days ago. It's ready for the merge window, which will open in a few days. The in-kernel support instead is still ongoing. There has been some preliminary work, so reworking the annotation of assembly functions in the kernel, which again has been queued recently for 5.7. And we're still working internally on the main feature, so setup pages, which will see the light of the list pretty soon, probably during the 5.7 iteration, so after the merge window closes. Big thanks to our friends from the GNU and LLVM toolchain, because there was a problem which was preventing the in-kernel BTI to progress in the past. So there was a problem with the fpatchable function entry support in compilers. This has been fixed both in GCC 10 and in LLVM upstream. So now this is all good, and the BTI enablement can progress smoothly. We are really targeting for all these security features the next LTS version, which will be the 2020 kernel LTS. This is the target for BTI. And also for memory tagging, specifically the user space enablement. So memory tagging, the last one of the big set of security features that comes with the 8.5 architecture, also called memory coloring, collaboration with Google, the Android team to consolidate and define this feature. The user space enablement, which allows Android to make use of it, is ongoing. We defined the ABI. The ABI is described in the documentation since 5.4. It describes the relaxation on how to pass tagged pointers to the kernel syscalls. Heap tagging support for memory tagging is ongoing on list, and there is a developers branch available again for reviews and initial testing. And the work is very much undergoing in conjunction also with the GNU toolchain team, because we really do want to test the kernel ABI against the proper glibc ABI as well before taking the patches upstream and merging the patches. So ongoing, targeting again, kernel 2020 LTS for user space enablement. The in-kernel support, the core changes for enabling the architecture, for swap and page table support are ongoing, for heap tagging only, again. If we are talking about stack tagging is a bit more tricky. So fine-grained stack taggings on coloring each function is known to break kernel single image. That will be really hard to accept. We are looking into alternatives for more coarse-grained tagging. But anyway, the current thinking is that this is probably going to be a debug feature, which is definitely pending compiler support for stack tagging, which again, we already know that will not come before 2021. So stack tagging will be a topic, probably a debug topic for 2021. Moving ahead again. New architectural features, SVE and transactional memory. SVE, the first version, the evolution of Neon, the Neon instructions has been enabled for quite a long time now, since 4.15 in the kernel, and into KVM starting from 5.2. SVE2, that's the enhancement of SVE, announced a bit more than a year ago, I believe, from the architecture, has been exposed to user space through hardware cap in 5.2. Not much more to be done in the kernel. It's mostly a user space work to make use of the SVE instructions. Transactional memory feature for lock-intensive operations, use cases like databases and so on, and JITs. There are some initial patches on list, which are against an early version of the architecture. Those patches will need to be revived and reposted against the consolidated version of the architecture. We haven't heard an immediate pull from partners or from the ecosystem around that. So we are not planning to revive the transactional memory support in the kernel anytime soon, unless we hear some strong requirements coming from partners and ecosystem. So if we take a broader look at what's coming in the next kernel versions, 5.6 almost stuck, and then 5.7, most of the features are already queued. So in 5.6, there are a bunch of 4 new architectural features that got enabled. One is an 8.5 E0 PD, so preventing EL0 access to halves of address maps. This has been enabled. And as I said at the beginning, the random number generator, only the runtime support has been enabled in 5.6, but we already got patches for the boot time support, so using RNG, which are queued for 5.7. So you can see them below. From the 8.6 architecture, we have, as I said, 2 little exposure to user space, bfloat 16 and integer 8 matrix multiplication. The kernel doesn't make specific use of this feature. It's just an exposure to user space. 5.6 will also include support for the ARM system IP, the new GIC interrupt controller interface 4.1. In 5.7, some of them I mentioned already, so a few things are already queued. So in kernel pointer authentication, there are the activity monitors extensions, which are queued for 5.7. PMU 64-bit enablement, so 64-bit counters coming from the 8.5 architecture, also included. Spoke about BTI, spoke about the RNG boot time support, and the last one I would like to point out is the memory hot remove. Memory hot plug also has been enabled quite since a few releases ago. The only bit missing was hot remove, and hot remove is now there. and will be merged into the 5.7 release cycle. It's not over. There are a lot of other enablements that we do related to ARM specifications. So let's have a quick look, really, into what are we enabling from an ARM spec point of view. The link here brings you to a collection of all the specs that our architects are producing on developer. So the first one is the PSA firmware framework, which I also spoke during the firmware talk. So this is about standardizing the way the normal world invokes secure services into the secure world. And it needs also a kernel driver for it. So the kernel driver is currently in development. The spec is expected to reach EAC by mid-April, and we will work very hard to stabilize the driver again on time for the kernel 2020 LTS. SCMI, power management interface, which allows the kernel to talk to an external power management controller, which on the ARM reference platform is the SCP, the SCP coprocessor and firmware, open source firmware. There is a specification that defines the communication process, and there are various step-by-step that are listed here. I'm not going to go into details. But have a look, and the latest notification support is on list and is linked there. Next one is the SMC calling convention 1.2. There is a new specific SMC that has been explicitly asked by partners, which is the SOC ID. Again, will be implemented very soon together with the publication of the spec. The one before last is a news. ARM is also going to produce a spec around the TRNG, which has been requested by the ecosystem. The spec will be released as beta beginning of April, and it will define standard kernel and firmware SMC interfaces for requests through RNG support and seeds for RNG generators. This support in kernel and firmware is still TBD because the spec is still in beta. We're still reviewing the spec, but the plan would be to would be to address those features in kernel and firmware somewhere in the second half of 2020. Last one, ACPI enablement. It's an ongoing story. The last one is regarding the CMN 600 PMUs. The spec is out in beta. Again, we reach EAC in April. And there is a developer branch ongoing, which maps the status of the spec. So almost at the end, there is one last topic that we have to talk about, which, as I said, is a highlight from a presentation from yesterday regarding Morello. The ARM Morello board, the prototype architecture, which ARM announced as an implementation of the Cherry architecture from the University of Cambridge. This is a wiki page on the University of Cambridge which describes the project, but I would like to point you to the presentation from yesterday from my colleague Mark Nicholson, which is listed there. He described all the step-by-step approach which ARM is taking for the Morello architecture, but focusing only on the kernel interesting bit. So there is going to be two steps. One is for October this year, 2020, there is going to be an MVP, a fast model release of the prototype architecture. From a kernel point of view, we don't plan any specific work on the extended ABI, the 128-bit ABI. We don't plan for it on time for the October release this year. The October release this year will be based on a Bionic library shim, which only expose some limited functionalities to an Android or Nanodroid stack for starting to enable some Android use cases. The real development against an extended ABI will start somewhere late this summer or this autumn timeframe. We are still planning for it, and it will be a combined development with the toolchain friends from both the GNU toolchain and the LLVM toolchain. The idea will be to agree on an ABI and arrive by the time the development board will be available in October 2021 to arrive with a proper kernel definition and with some patches that will be hosted on some separate Git repo. This is not meant to be an activity to be merged upstream as we go all immediately. This is a prototype architecture with prototype ABIs, which will enable some exercise from the community to really exercise the architecture and see which are the benefits and the costs of the implementation. I put some useful resources, which we can go through offline. And that was basically it, unless there are any questions. Almost out of time.
There are a couple questions in there. If you think you can answer them really quickly, you can go through them, but we do have to set up the next person in the next couple minutes.
Right, let me see if I can see the questions at least. Yeah, for some reasons it's not opening the chat window. Can you read them? Oh, maybe here. If you can share on the npam CPI spec update availability. Yes, this is mostly a question for our architects, but I believe it will come somewhere late 2020, probably in the second half of 2020. That should be the idea. And what support are you planning for it? There is DFM update, please guide support for the this might require a more complex answer. So I guess we can probably close it here, and I can follow up offline with the guys that have more complex questions, and we can bring the conversation offline.
Great.
It's probably be easier.
Great. Well, thank you, Matteo. That was great. Thanks everyone for attending and all the people watching on YouTube.
Thanks, everyone.
Thank you. Okay, Paul, you can go ahead and get started whenever you're ready.
Okay, thanks a lot.
Thank you.
Okay, welcome to the status of TensorFlow on ARM-based HPC. Now, what we're going to do is not cover the detailed workflow of what TensorFlow is. I'll give you an overview of that, but specifically how we're making progress in running TensorFlow in an ARM-based environment. So we're also looking to encode TensorFlow on AArch64 in such a way that it is optimized for the various ISAs. So whether your silicon is running 8.1 or 8.2 and potentially 8.3 soon for some people, maybe. We want to ensure that each of the commands which are hardware benefiting or benefiting by the new hardware, that they are incorporated into TensorFlow optimizations. But rather than just leave it at the library, we're also going to see how we can use TensorFlow in a real world application, such as an artificial intelligence solution. So this is the work that is ongoing currently in a group called AI on Servers, and that's a collaboration with our other project members called AI/ML group as part of the overall Linaro's project collaborative approach to artificial intelligence. So currently TensorFlow does compile and run on AArch64 hardware. So problem solved. Okay, we can go. Everything's sorted. Actually, it's not quite right. It does compile if you've got specific versions of libraries. So the underlying dependencies, if they are there. But the moment you start modifying those dependencies, then the specific version of TensorFlow may or may not compile easily. So what do I mean by that? Well, let's just point out what TensorFlow is anyway. I said I wasn't going to go into the absolute details, but it's a method of creating from scratch machine learning models. So you may hear about edge devices using machine learning models, but where do those models come from? Well, they're created in training sessions or model creation sessions using frameworks such as TensorFlow. Others could be PyTorch or DNNL, or maybe they're hand-coded. But the difficulty is that you basically not just need to be a data scientist, you also need to be a software engineer to encode the training of these models. So it's quite complicated. Now, we know Google is trying to address this with Google Cloud functionality. And what they're doing is automating as much as possible the process of selecting data, refining the data, training the data, and optimizing the resultant model. So that's fine when you're using generic models or generic environments, but what happens if you've got a bespoke solution that you need to encode? Well, it's back to hand coding in either Python or C++, calling to the relevant libraries to do so. Now, an extra tool which you may require is if you've got the data coming in to your data set in not an ideal format, then rather than hand coding every single line concatenation or string chop as required, then there's a tool called Keras, and Keras can help to align the data into regular text formats, of which is more easily consumed by TensorFlow. Now, TensorFlow generates models. Now, those models could be several layers deep or include several neuron or nodes within each layer. But how many do you actually pick? Is it randomly selected, such as 5 layers with 6 nodes each? Maybe it's 6,000 nodes with 10 layers. To try and figure out what would be the best approach isn't always easily done by hand. And so looking at ways that this could be done, we can follow AutoML principles. And there is an application called Keras Tuner, which is for hyperparameterization tuning. And what that does, it specifically looks into number of layers or number of nodes within each layer that is required within given ranges. Now, that sounds great, but we started out with a title about TensorFlow and HPC. Well, why do we need HPC? Well, if you start to think of the number of possibilities of layers, nodes that could be part of a particular model, plus the size of the data sets that you're likely to be crunching to actually define the model, then you're going to need a high performance computing system to be able to do that training. So the number of iterations when you're tuning grows significantly. So this is why we need TensorFlow and the other frameworks to be available within the HPC environment. Now, we know they are in the x86, but we're in an ARM-based conference, so we'd like them to also be first-class citizens in the AR64 environment. So the particular versions we've been looking at, so the last version of version 1.15 or 15 was released in the middle of last year, and there will not be any further version 1 being released. And as of earlier this month, version 2.2 has been released, and we understand that there is some conversion issues going from version 1 to version 2. Now, as of a few days ago at the TensorFlow Dev Conference, there was an implication of that 2.2 will actually be a little bit more backward compatible to the existing 1.15 libraries. So we need to investigate how more easily it allows you to do the translation between the older versions. And the reason for doing so is at the end of this year, Google will actually stop training jobs on version 1.15. They are, in essence, forcing you over to the version 2, which can be a good thing because moving over to whatever the latest and greatest is can offer benefits. Now we have to highlight that there's been a little bit of reluctance initially moving from version 1 to version 2, simply because of benchmarking. Now, benchmarking, so if you want to sing the praises of the particular system you've got, you want the best performing benchmarking. But apparently in version 1, the benchmarks work better in than version 2. So you can understand the reluctance to not want to do the latest benchmarks highlighting version 2 performance. This is something that we just need to encourage the transition over, and where there are optimization issues, then that's where we need to look into them. Now, I say we want to make ARM64 the sort of first-class citizen for TensorFlow. Because if you actually look in the TensorFlow community builds, then you'll find sort of quite surprising results. So in the official builds, the only time ARM64 is mentioned is as Raspberry Pis. And we started out this conversation by saying, let's put TensorFlow on HPC. Don't quite think a Raspberry Pi is up to the I/O characteristics of high performance computing, but fair's fair. It's a server function, albeit a very small device. So we don't mind it being on there. It's just that we'd also like things like ThunderX2 to be on there, maybe A64FX with SVE on there as well. So rather than just the particular chips, it's the entire system. So over the last couple of weeks, we've had announcements of ThunderX3 and then the Ampere Ultra So the Ultra being 80 core and the Thunder X3 being 96 core with multi-threading. So these are significant devices, significant silicon that can be put in service chassis and scaled to high performance computing levels. So it makes sense that we try and apply some pressure or talk nicely to Google to say, come on, can we have the official builds, please, for TensorFlow on ARM64. Of course, sometimes we're driven by community rather than just the official builds. But if we look at the community build status, then we see AMD's ROCm GPU, we see the PowerPC GPUs and CPUs, and we see Red Hat Linux at version 7.6 on CPU and GPU in x86. Because it's a little odd. We see Red Hat just at the bottom there, simply because if we just go back, you'll notice that what you're not seeing, it just says generically Linux CPU and Linux GPU. But if you look at any of the recipes on Google searches on how to build TensorFlow, more than likely you're going to find that they're Debian builds. Okay, and quite specifically on the Raspberry Pis, they're Debian builds. What Linaro likes to do is encourage distro agnostics. Whilst, of course, we accept Red Hat is very much a member of Linaro, and it's great news. We want to make sure that what we develop applies to all major distributions as well. So we like to encourage recipes which allow Debian, Red Hat, SUSE scenarios to be listed on these sort of build status. So let's see if through encouragement we can increase the number of items on these build status lists. But we are limited in what versions are required, because TensorFlow requires the build system from Google called Bazel. And Bazel has its own dependencies. And currently, the latest shipping version is release 2.20. However, we are using something like 0.89 as a release level, simply to try to get TensorFlow to build on AR64. So a 0 release, you can imagine that there's going to be some difficulties or some features which are not carried through to the latest solutions. So we'd like to sort of work with the community so that we can fix all the issues between what is preventing Bazel to be loaded. So we ask the community to get in contact with us and assist both in the TensorFlow builds itself and the underlying dependency of Bazel. So the application of what we're looking for TensorFlow. So we have a group called AI on Servers within the HPC group. And so we collaboratively go with the Edge device team that are looking at AI/ML. And we look at more than one framework. So we have TensorFlow and PyTorch, and we're also looking at DNNL and the integration of DNNL with the above frameworks as well. So we're focused on the data center. So I'm director of the LDCG, or Data Center and Cloud Group, and we'd like to see our high-performing ARM64 devices doing the training primarily. They can, of course, do inferencing, but if you're out at the edge and you're unable to carry a 2U chassis around with you, then of course you want the edge devices, the smaller devices, to actually do the inferencing. So we look at the reinforcement training to make sure that what is being modeled is effective. And if it's not, then we feed back into a feedback loop, an iterative feedback loop, to tune the models effectively. And we're looking sort of beyond ML as well. So we understand that TensorFlow is primarily a machine learning environment, but ML is a subset of AI. It's not a superset of AI. And so we're looking at the broader range aspect of AI on servers, of which ML and TensorFlow would then be an operational part of it. Now, we have some resources available, and we encourage community assistance as well to optimize TensorFlow and the various libraries for SVE and the upcoming SVE2. Both are supported in the GCC and LLVM compilers already. So you don't actually need hardware to run these particular versions. You can use software emulation models so that we have the software available when the silicon is also available. And the key difference also for AI on servers is the online dynamic approach. So conventional models are trained by throwing a whole load of data at the training environment, and then working on the model. And once the model is done, you take the model and you use it. But if the data structure changes, you have to throw away that model and start with a whole new data set and do a complete retrain to generate a new model. Now, each new model could take hours or days or even weeks if you're talking about billions of layers or billions of data items in which to calculate. And then this is also why we need HPC or exascale computing even for the very large data sets. But really of interest is the online dynamic nature of the potential for AI learning. So you actually report back on, such as say a reward mechanism, if something is identified correctly versus a negative reward system if something is identified incorrectly. And so that over a period of time, you can tune the intelligence that is being utilized. Now, we don't just look at frameworks, we look at underlying libraries, and we look at OpenCV, OpenCL, and OpenMP. Each of those need further optimization to make use of the SIMD architectures, such as the earlier versions of Neon, and then subsequently SVE and SVE2. So we'd, again, like community support from that, for that. And these are the sort of environments that we're looking for training methods. So this is where we can apply TensorFlow in straightforward image classification. We've heard about the 11 million cats to identify a cat, whereas a child will be shown maybe one cat over a period of time and realize that over a period of time that it's called a cat. So there's a differentiation between massive data sets and learning like a child. So object detection, we see the automotive industry doing some collision avoidance systems where they know they've got models which identify what cars look like, what pedestrians look like, cyclists, etc. But we're looking to see if we can get sort of TensorFlow to move beyond just those basic object detections and look at the further AI a more intuitive way. Because what happens if a new car design is brought out that doesn't look like previous car designs? Well, you have to go back to the drawing board and do a whole new set of data to recreate the model. Yet a human's observation of a new car would think, okay, it's new, but overall, fundamentally, it looks like a car. And so this is the area between pure computation and a bit of intuition or understanding. So at the bottom of the screen, you see perception, understanding, discovering, prediction, creation. These are the approaches as to where we want to really push the underlying libraries. And if we can get them to so not just rely on HPCs, but maybe the HPC is in the cloud and the edge devices are doing the latency sensitive solutions, but then the edge device is referring back to the cloud to receive updates. And in fact, there's a company, I think Neurala, they offer a cloud solution talking to edge devices, which do pretty much that. The edge devices feed back changes to the model. The model is recalculated in the cloud, and then the cloud re-downloads back the updated model. we don't really want to test all these things out in the open environment. It could be a little dangerous having a robot running around a roadway. So we like test environments. So here's a list of 5 different sort of AI environments, the DeepMind Labs, Google Researchers, the Habitat from Facebook, NVIDIA's Isaac SDK, coincidentally, so Paul Isaac, but nothing to do with me, and the Cyberbotics Weebots. So we'll be looking at proving the optimization, first of all, of the TensorFlow library, but then the application of that library, how it performs in these test environments. And so if you're looking to actually test any of your own codes, we can look at hosting some of these potential environments. And we host these things in our co-location facility, currently in London, and some elements of it in the US as well. And we encourage developers who want to try their solutions on ARM hardware, ARM server-based hardware, to get in contact, and then you'll be able to test your solutions on the large HPC environment that are typically run. Now, to give an example of a large HPC, which is ARM, well, Sandia National Labs, they have the Astra solution. And then we have Fugaku running the A64FX, which is currently being constructed in Japan through Fujitsu and Riken. Hopefully we will get access to those as well. So where are we technically? So just as a sort of a wrap up. So we're currently reconfiguring our hardware in the co-location facility. We're looking to have a truly scalable environment. So we can go from a small number of nodes to a large number of nodes, depending on the build scenario that's required, and then scale it back down to be sort of efficient use of the energy, so electricity. And ARM is helping by providing some of the build recipes for TensorFlow and MLPerf, and so we work alongside all our members and their member engineers, so that it's not just Linaro coming up with sort of the software or the build scenarios, that we actually encourage a collaborative environment. And we will obviously recognize where the source of the solution came from. So we are currently reviewing our own TensorFlow continuous integration solution. To be fair, we've got a couple of issues with Python 3 in the build, but that's ongoing. However, you can see our GitHub page if you'd like to contribute. I made reference to a GitHub page on a previous slide also for the AI on servers, in case you've got some examples that you'd like to upload. And what we're currently been doing also is just making sure that OpenCV works on AR64, which is very, very easily done because it even works on the Raspberry Pi. But we'd like to scale it up in optimization. And we still have plenty of things to do. So OpenCL, OpenMP are required. We've got some test platforms for the new Neoverse N1 solutions, which will be the ISA version 8.2, whereas the current shipping hardware is 8.1. So it's a benefit to have those available. And then we do plan to test containerization so that we can improve the scalability of their build scenarios. So with that, if there's any final questions, other than that, please feel free to contact us on aionsservers@linaro.org, or offer to submit on the GitHub page any of the examples. Thank you very much.
Thank you, Paul.
So if we just look at some of the questions, I see. Is there a TensorFlow 2x package or Docker image available now to run on ARM64, and where can I get it from? I personally don't have the Docker images available. I know that NVIDIA has been containerizing elements of it, but it's something that we do want to get into, but we don't have available yet. Okay, is that the only question?
I think that might be it.
Okay, thank you for your time then.
Thank you, Paul.
Hi, Christine. Thomas here. Should I take over the screen?
Hi, sure, you can take it over whenever you're ready.
All right, just so I can try that this works here.
Okay, we can see your screen.
Okay, good.
And you can start whenever you're ready.
All right, so let's get started here. So good morning, good afternoon, good evening, everyone. My name is Thomas Evanson. I'm from Xilinx. I'm going to talk about system device trees today, together with Stefano Stabilini and Bruce Ashfield. So we have lots of material, so we'll go through this pretty quickly here. Obviously, the slides are uploaded, and there's some contact information at the end if you want to engage in this. The way we have set up this is in a form of frequently asked questions. So instead of going through all the various slides, and we've been doing that in various contexts before, we thought that instead we will mix it up a little bit and answer some questions around device trees. And the first ones are more general and will serve as an introduction to system device trees as well here. So if we get started here, if I can figure out how to do that. Okay, so maybe, whoops. I have this on top of the other one. Let me figure out how to do this. Share. Seems like my screen is on top of my presentation screen here, so I have to figure out how to do this. Oh. Sorry about this. No.
Do you want me to try to share them and then I can just click through for you?
Yeah, or maybe Stefano, if you're there, can you share them? I don't know what's happening here when I'm.
I can certainly do that. I don't know if I have the very latest version, so I have the one from yesterday. Is that okay?
Yeah, that's okay. It's just one slide at the end there. Sorry about this.
Okay.
No worries.
Just a second then. Can you see the slides?
Yes. And if you can go to presentation mode there.
Yeah.
All right, great. So first question here, what is a system device tree? So if you jump to the next one there. So system device tree really trying to solve the problem of how do we get hardware information to the software stacks. So in particular, operating systems, firmware, hypervisors, those kind of things that need to know about where is the memory, what memory is allocated to me, where are all the devices, where are they mapped in memory, the interrupt, so on and so forth, right? And in particular, these new systems that are out there now are very heterogeneous. So you have multiple processors and they have multiple execution environments. So you might have a Linux running at the same time as an RTOS, at the same time as a hypervisor, and so on and so forth. And so we need to come up with a way on how do we get all this kind of information to these different software stacks. And this is really tricky to do in general. And in the past, it's been done in an ad hoc way. So what we really need here is a standard way of doing it. So if you go to the next slide. And since there already is a standard that really serves us well, which is device trees used by Linux, U-Boot, Zen, hypervisor, and other things. What we wanted to do was to extend that to be able to handle multiple different environments at the same time. Right? So we're extending the device trees backwards compatible so that you can have multiple CPU clusters and you can define how you want to share things. And we really have two different parts here. One is adding to the traditional device tree specifications. You can add new CPU clusters and their views of the addressing space and so on. And then we're also adding a section so that you can define the allocation of resources. So let's say that you want to have 1 gig of memory going to your Linux and another gig going to your RTOS, or you want to have the NIC assigned to the RTOS, but the UART assigned to the Linux. So there's a way then to specify those things. So those are the two sections. We're trying to separate that a little bit. So one is more of a describing the hardware, and the other one is more about how do you configure it? How do you allocate the resources? All right, go to the next one. As part of this, we are going to talk about something we call execution domain. So it's going to talk a little bit about that here. So if you go to the next one. So an execution domain, pretty simple concept. In general, you can view it as an address space that's unique and different from other things. So for example, a Linux kernel has an address space. So that would be one execution domain. If you have a hypervisor like Zen, well, it's running on the same CPU, but it actually has a different view of the memory and the devices. So that would be a different execution domain. So an execution domain could be running on a separate core, for example, if you have a Cortex-M or Cortex-R versus a Cortex-A core or multiple clusters. It could be on the same core, but that you have different execution levels. So the user space versus operating system and hypervisor and the trusted firmware and so on. And you also have a way of dividing your address space using trust zone. So a trusted execution environment would be, for example, a different domain than your Linux, as an example. So the domain is really the address space, the view of the memory, and an operating environment is really the operating system or firmware or hypervisor that's running within that context. Okay, moving to the next. And I think, Stefano, you take over here.
All right. So what's the difference between system device tree and device tree? So concretely, system device tree needs to be able to describe more, to describe a full platform with heterogeneous CPU clusters. For instance, a platform with a Cortex-A cluster and a Cortex-R cluster. And also to describe execution domains in the way that Thomas just introduced them. So for the first set of description, so the hardware description, actually we can do everything with these three new concepts. So these are three new additions to the device tree spec that allow us to describe these heterogeneous systems. So one is CPU cluster. Of course, you need a way to explain, to describe that there is more than one CPU cluster, and that is what this attribute CPU cluster is for. Then it might be that certain resources, a bus, a device, is only accessible, is only wired to one of the two CPU clusters, or one of the many CPU clusters. And that's why we have indirect bus, which is a new type of bus that does not automatically map to the parent address space. It means that it's not automatically visible. And address map is to explicitly map these resources like indirect buses, so that you can explicitly say that this resource is actually visible from this domain and not from the other. So I'm going to show you a concrete example. So here we have still the usual CPU cluster. The default cluster could be the Cortex-A cluster, where Linux runs, for instance. And then we have another cluster here, a Cortex-R5 cluster, which is compatible CPUs cluster. And finally, we have a bus, an indirect bus. So the idea is that this bus is only visible by the R5 cluster. So to do that, we specify that this indirect bus is compatible to indirect bus, of course. And also we explicitly mapped it into the Cortex-R cluster address space using the address map property. because it was non-mapped, there is no address map property in the default cluster. There could be, but it's not used. Then the bus is not visible to the default cluster. So speaking of default cluster, so one question we might have, why still have it? I mean, if we go back, you can see, I mean, clearly we could have described the system using 2 CPU clusters in the new way, right? This new compatible string. Well, one reason is that it's actually convenient to have one default that owns everything, but everything is assigned by default. It's also very common in many configurations when there is a Linux system that has all resources except for a few. But also, this is a more subtle, but maybe more important. It really turns system device tree into a natural addition on top of device tree. It makes it much easier and simpler to introduce these new concepts like the one I just discussed on top of the regular device tree specification and add them themselves to the specification. Finally, it gives us a chance to maintain backward compatibility with existing systems. So with the default CPU cluster, it is conceivable to produce a system device tree that describes more than one cluster, but still where Linux is able to boot. All right, so there are a number of questions that we usually get on system device tree, and one of the top one is, how do we describe interrupts? So, you just showed these 3 new concepts. There is nothing about interrupt there. So let's start by explaining how do we describe interrupt controllers. So in an heterogeneous system, typically like the one we are using as an example with a Cortex-R cluster and a Cortex-A cluster, each cluster is going to have its own private interrupt controller. And to be able to describe that, we need to be able to show that one interrupt controller is only visible by one of the 2 clusters, and the other interrupt controller is only visible by the other cluster. And we do that using the same address map and the indirect bus trick that we used before. So in this example, the Cortex-R interrupt controller is under an indirect bus, which is only mapped by the Cortex-R cluster. Vice versa, the Cortex-A cluster interrupt controller is under a normal simple bus. That means it's going to automatically translate to the parent address space, so the default cluster will see it. The Cortex-R cluster will not see it because it's not explicitly mapped using the address map property. So this is a technique that is generally applicable, and you can use it to describe any kind of resources that are only visible by one of the cluster, not visible by the other cluster, or by a subset of clusters, to really describe how the whole board has been wired. What about interrupts themselves? This was about interrupt controllers. So typically what we want to show is a resource as interrupt that are wired to go to both interrupt controllers. And then, depending on configuration, only one of the 2 clusters might still receive the interrupt, but term of wiring, it goes to both. And we can do that using the existing standard properties, interrupt map, interrupt map mask, and interrupt map pass-through. This is the way they're described in the device tree specification today, so this is not new. And this is saying that basically this CAN bus interrupt, which I picked just as an example, it goes to both as 2 parents interrupt controllers. So it goes to both the interrupt controller of the A cluster and to the interrupt controller of the R cluster. All right, so this tells us how to describe most hardware configurations. But what about how we configure the system, the software, the firmware, to assign resources, to dedicate resources to CPU clusters? So this is not about wiring, this is about the execution domain configuration. So let's look in details about execution domains. So the idea, each domain has is specified where which CPUs is related to. So where the software is running specifically, what memory region are dedicated to them, and what devices are dedicated. The way it's described is using this format. So there is a CPU attribute that tell us which are the CPUs where the software is running on. In this case, a Cortex-R cluster. There can be special flags to explain, also to describe the execution mode. lockstep, non-lockstep, and also the execution level. Then a memory attribute that tell us which memory region have been dedicated to the execution domain. That it can be more than one range, like in this example. The second range is just one page. It is meant to show that you can use this simple technique also to describe shared memory regions between multiple execution domains. That way, you can set up a page with a ring buffer for communication. And finally, maybe most important is the access list. The access list is a list of links to resources that can be accessed by this execution domain, possibly only uniquely accessible by this execution domain. So before I dig more into what that means, I would like to point out that in this example, there is a new top-level node called domains. The purpose of that is to collect all these execution domain configurations. So given that these are software and firmware configuration, it's good to keep them separate. And originally, we were proposing, adding them under the chosen node. However, for reasons that will become apparent soon, although it's still feasible, it's cleaner and better to have them separate. All right, so how do we configure bus firewall? So often, in order to dedicate, if you really want to dedicate and protect a device, you will really need to configure the bus firewall to do it. So the idea is that out of the information on the system device tree in the execution domain configuration, it is possible to generate the bus firewall configuration. So this is the information the bus firewall needs, just not in the format that the bus firewall needed. So the idea is that we could write a plugin for Lopper, the tool that Bruce will introduce soon, to parse system device trees, to generate out of this information the appropriate bus firewall configuration. If you can see here, there are memory ranges. You can find all the information from the link about the MMIO region of the device. So all the information is there. So there is one thing that's missing that we have been thinking about, and I'm telling about this more like a problem statement. We don't really have a defined solution yet, but often bus firewalls don't have that many slots. So it is common to have a configuration where there are more devices to protect, more domains, than the amount of slots the bus firewall has to protect them. So in these scenarios, we have to make the difficult choice of protecting only the most important devices and the most important domains. And that's why I think we need to introduce something like priorities, like a priority per domain, to say this domain has a higher priority than this other domain. It should definitely be protected first, like maybe a safety critical domain. But we might even need higher granularity, such as per memory range or per device priority, to be able to say this device actually has a much higher priority than the other device. Yeah, we'll discuss priorities in one of the next OpenApp calls. All right. I have only one last point here. That's about chosen and reserved memory. So chosen and reserved memory are firmware and software configurations. They exist today, they're top-level nodes. For instance, chosen has information about the command line arguments for Linux. So in system device tree, they still exist, and they still have the same meaning that they have today, meaning that they are software configuration of the software running on the default CPU cluster. So the Linux running on the Cortex-A cluster, if that's the default cluster, it will still get the argument under chosen. However, other execution domain still need their own, potentially they need their own command line argument for the operating system running there, or they need special memory reservation for special drivers like reserved memory does. So we need another chosen and reserved memory node under each domain to express these configurations. So the idea is that each domain will come with all the configuration needed for the software running on top. And that's the end of my part, and I'll let Bruce continue.
Yeah, hopefully everybody can hear me. I've been having some network bandwidth issues this morning, so I'm not going to turn my video on for safety reasons that I might disappear. So I'm going to do a very quick overview of what is LOPR. If we can jump to the next slide, Stefano. So it's something that we've been poking away at, and I've been working on since probably May of last year. And it's a tool for manipulating the system device trees because they can be quite large, and we're trying to eliminate some of the errors and manual editing and supporting these different workflows of different people working on a system device tree as it goes through a system. But the primary goal that we had, when it started and as it still exists, is that it's to produce a standard device tree to support existing platforms and operating systems. So, it inevitably you can take a system device tree, and the default that comes out of LOPR is a device tree that Linux or anything that's used to parsing or manipulating a standard device tree, it won't have any elements that it doesn't understand. So you don't have to modify every operating system immediately to work with a system device tree. It is data driven. It doesn't fundamentally understand system device tree. I have a slide that shows a few of the inputs very quickly. So there's no hard-coded logic in the tree. It works on various inputs, and it uses plugins and operations to do anything from generate code, do custom outputs, or do device trees. It is going to be, it's open source. It's under a BSD3 license. I have the link to where it will be probably by the end of the day. That's a landing page which will be updated to the code where it will sit on GitHub or whatever we put it under. It is literally just Python and libftt and the Python bindings. It works with DTC to compile device trees, but then after that, it works completely on DTBs at the moment. And we're exploring different ways to manipulate the back end, but right now that's sort of, it's using as little as possible to be as simple as possible and portable as possible. It also, there's modes where we can output device trees, and it performs extra validation and consistency checking during output. So if you end up doing something that drops one of your P handles that Stefano was showing in the access node, it knows how to either notify you or make corrections through the tree on the way out. All right. So yeah, we can jump right. I just had a slide here that shows what are the different parts that go into LOPR. And fundamentally on the left, it is only, we didn't create anything. They're all standards-based inputs. So whether they're system device tree or normal device tree, DTS files or overlays, and these LOPs, which are LOPR operations. And they're also actually specified right now in a device tree type format. And then you see in the middle what LOPR is. It's Python, DTC, CPP, everything that you'd expect, with a bunch of different sort of backends where you can say go back to DTS if you want to manipulate the source more. You can do DTB to C if you want to generate C device drivers for an RTOS or bare metal, or it can do a custom bus firewall specification that Stefano was talking about. So the point is that it's using open source inputs. It manipulates a device tree, and then it has various backends to do whatever output you may need. So I just did a quick capture of, the question is, how do I run LOPR? As I mentioned, that's the primary goal, is to create a traditional device tree. And it's, it pretty much, it takes a system device tree, it takes a domain node as inputs, and then a bunch of LOPR operations, whether they're custom or built-in. It outputs a standard device tree. So what it does, and the flow is always, it applies operations to the tree as specified in the operations file. It finds a domain node. It can call an assist or do basic operations on those domain nodes, which will manipulate the tree. And then it outputs the modified system device tree. You can either do it as this sort of raw DTB dump, or you can validate the tree on the way out and go back to source. But either way, the output is a standard device tree. Oh, and this, yeah, it's a bit small, but it's more here for reference. This is just an example run where we're taking this R5 domain that Stefano was using as an example, a system device tree for a Versal, and it's outputting a Linux R5 DTS. And you can see the run, and there's some things here where it knows how to, it had two different CPU clusters, it deletes one, it renames some nodes, it does, and then the bottom part here, it's writing this output DTS, which I can see I left foo.dts in there. And it does validation, and you can see that it's doing some p handle replacement and validation of the tree on the way out. And just in this example, I just grabbed a couple things that the system device tree on the way in, it had 84 elements, if you will, just a block in the device tree that was had a label. And after we've run it, we're now, we're down to 41. So it dropped half of the system device tree. And for example, before we started, the CPU's node was the Cortex A72. And after we run it, which is the right-hand side, it's now been renamed as the default CPUs are now the R5s. So it knew as part of this manipulation to drop the A72s, it kept the R5s and it renamed them to CPUs as the default boot, say for a Linux or whatever, would only be looking under CPUs. And the question is, what about an RTOS or something without device tree support? What can you do? And so again, same inputs, always a system device tree. You don't need a domain node in this case, potentially, LOPR operations. And what in this case, it does applies the operations, processes the tree. And in this case, it will always put out the device tree that was a reference, however it was changed, but it has an OS specific module that outputs, in this case, some C defines and some code based on the modified device tree. And I just did a little snippet of an example that I ran one where I was doing a safety critical device tree, and we took the Versal and we wanted to output the RTOS header.h. And so in this case, it knew how to modify the device tree. It made a bunch of defines with constants that were left as a sample. And it also was putting out and implementing some structures based on what was left in the field. So that's completely flexible. That's just a Python assist that I wrote to show how easy it is to modify a device tree and then print out C code as an example.
All right, I think we're out of time. On the slide deck that's uploaded, we have an extra slide that talks about how you can engage with system device trees. So this is a project under the Linaro device tree evolution project that's going on in Linaro. And it's under the OpenAmp umbrella. We're driving the system device tree. And there's a couple of links there so you can get in touch with us, and there's a mailing list as well. So thanks, everyone.
Thank you.
I guess we have one question. There is an address map property new for system device tree. So Stefano, maybe you can take that.
The address map property is new and was one of those introduced specifically for system device tree. Yeah. It's meant to map, especially indirect buses that otherwise have no way of being mapped into the address space of a CPU cluster.
Great, thank you.
Thank you all.
Okay. Bye-bye.
Thanks, bye.
Hi, everybody.
Hello.
Hello. Hi, Christine.
And feel free to take over the screen whenever you're ready if you want to share any of your slides.
Okay. That was going to be my question. Good. So can everybody see this? I put it in full screen mode.
Yes, we can see it.
Great. So Christine, when should we start?
You can go ahead and start now.
Okay.
Thank you.
Samir, are you there?
Yes, I am.
Great. Okay, hi everybody, and welcome to this session, which we called Is Your Pi Server Ready? And of course, we're referring to the Raspberry Pi 4. And this session will be about embracing ARM server standards at the edge. My name is Andre Workington. I'm a tech lead for the ESXi ARM project at VMware.
And my name is Samir El-Haj Mahmoud. I am a system architect at the ARM Architecture and Technology Group at ARM.
And so the rough agenda today is we'll briefly mention what ARM Server Ready is. We'll talk about single board computers. We'll briefly go over how we are prototyping this with the Raspberry Pi 4, mention some challenges, show you a demo, well, a very static looking demo, and provide a brief call to action.
All right, I'll start by talking a little bit about the ARM Server Ready program. So in the server market, which is a horizontally integrated market, there is a need to design systems that just work for the end user with the ability to install and run standard off-the-shelf operating systems. And in order to do that, there are a minimum set of hardware and firmware requirements that need to be followed in designing such a system. So for the ARM ecosystem, this need first arrived in the server segment. The ARM Server Ready Compliance program was introduced to provide this just works solution for servers. The program provides blueprints for designing ARM servers that are based on industry standards, such as some of the hardware and firmware standards like PCIe, UEFI, and ACPI, as well as ARM-defined requirements and standards like the SBSA and SBBR, which we will go over in more details. In addition, the program is accompanied with a compliance test suite, we call it the Architecture Compliance Suite, or ACS, and a process for certification. The goal is to have the ARM servers just work with off-the-shelf operating systems, at least enough to use a standard OS image to be able to install, boot, and then can install missing drivers and software packages. So it behaves in a familiar way to the ecosystem, OEMs and ODMs, software developers, and IT staff and customers. Next slide. Yes, thank you. So the first main component of the ARM Server Ready program is the server-based system architecture, or the SBSA. The SBSA specification covers the hardware requirements for servers. That includes requirements to run these standard operating systems based on both industry standards as well as ARM standards. So that covers a range of requirements for the processor, memory subsystem, the interrupt controllers, the serial controllers, the serial port controllers, PCIe, device integration and implementation, etc. So there is Coverage for PCIe, of course, as an industry standard. In the future, you may see other interconnect technologies like CXL or C6 included in this standard as well. But there are also reliance on ARM architecture hardware standards, including the ARM architecture itself, the extensions for RAS, and other specifications from ARM. The SBSA was designed to have multiple compliance levels, starting with level 0, which is least interoperable, mostly implementation defined, and then goes all the way to level 6, with each level being adding additional requirements and raising the bar with additional functionality. And if you look at the next slide as an example, for level 6, you can see that there is traction on adding more requirements that map with, for instance, additional functionality and features added to the ARM v8 architecture. And you can see here from just the sample of requirements that are introduced in these levels is that they span from the processor or PE processor core requirements to on-chip I/O and even system level design requirements. For example, in SBSA level 6, we added an appendix that show how PCIe is properly, including endpoints, are properly implemented and presented in the system, including things like the ECAM or the enhanced configuration access method implementation. So that's the SBSA. The second and equally important specification that's part of this program is the SBBR, the server-based boot requirements. Similar to the SBSA, which is a set of requirements for the hardware, the SBBR focuses on firmware requirements for operating systems and hypervisors, leveraging industry standards like UEFI, ACPI, SM-BIOS, PCI firmware, and the TPM interfaces from TCG, for example, as well as the foundational common elements from the ARM firmware architectures, including the PSCI and other interfaces provided by the trusted firmware. These set of interfaces, if implemented, offers the standard boot handshake to the operating system, as well as the required runtime interfaces for discovery, power management, and other functions. Now, so everything we talked about so far is server-ready servers, server-based architecture, server-based boot requirements. So you may ask, well, how is this related to the Pi? Since this session is talking about the Raspberry Pi. Oh, that's exactly what we want to get out of this session, is that the approach, the standards-based approach that was taken first in the server segment can equally apply in other segments where you want to achieve this interoperability between players, including operating systems, silicon manufacturers, and OEMs or device manufacturers. So think of it as standards based rather than server based. In today's beyond servers, the ARM ecosystem is by nature is very diverse. It covers many verticals, from embedded, IoT, automotive. It's really a wide range of devices, and with that diversity of the classes of devices, you have a diversity in the solutions, so being the hardware solutions and the firmware and even the operating systems. In the embedded space, even as we talk about higher end edge devices that have higher capabilities in the processing power, the ecosystem is still mostly treated as embedded devices that are vertically integrated ecosystem, running custom firmware and custom operating systems, usually Linux kernels that are customized for that device. By having these devices behave as embedded systems with custom operating systems, you lose the ability to, for example, get updates, security patches, and interoperability of add-in devices and switching OSs and hardware, the kind of flexibility that you have in a horizontal ecosystem like in servers.
So is there a light on the tunnel? Can we do something about this? It seems that standards shouldn't be just for servers. And if you look at the other architecture, they clearly aren't, right? And at the ARM TechCon 2019, we saw ARM extending the idea of server-ready compliance or standards compliance to other segments, where conceptually it allows off-the-shelf system software to run on a wide range of systems. Now, so really, it's not about server requirements. It's more about different kinds of standardized or system requirements for the same class of, say, compute elements, right? In this case, we're talking about what's known as the A application profile ARM systems. Okay, so what systems do we have there? Well, we have servers. Okay, that's pretty easy, right? Those go in data centers, cloud. They go into infrastructure, edge, network equipment. Then, of course, we have client devices. So that's laptops, tablets, edge devices, could be IoT gateways. And there's no reason why today these are all widely or more or less widely incompatible. I can use an x86 laptop, $200 thing, to develop an operating system that will boot on a high-end server or an application. I don't have to worry. They may be implemented very differently, but from a system software perspective, from an IT perspective, really, they are equivalent. And so for ARM, it'll be pretty fantastic to have a common standard definition across a wide range of these A-profile chips, A-profile-based solutions. It could be based on the existing server-ready specifications, such as the SBSA and SBBR that Samir talked about, or the security specification. Now, clearly, servers and non-server systems, while they may have a large degree of commonality, they will have, of course, places where they diverge simply by the requirements. Again, it's not inconceivable to imagine that you could see a common set of specifications and server and edge and client adaptations to those that would actually go and be more stringent for servers, maybe, or relax certain aspects, or define even different requirements for client devices, where, of course, if you look between laptops and servers, there are different requirements there, right? So obviously, we've heard about EBBR before. It sounds like EBBR could be kind of the solution, right? And EBBR is the embedded base boot requirements. However, what EBBR accomplishes today is it basically says that the boot firmware interface should act like EFI, and maybe that's real EFI. as in like a full-fledged implementation, such as based on Tino Core, or that's an implementation based on U-boot. Okay, but it doesn't talk about how hardware should be interfaced or described. Okay. And a good example of an EBBR system would be a Raspberry Pi that boots with U-boot and flattened device tree, right? Which allows an EFI OS loader such as Grub to be used. Another example that I will claim is EBBR, that's just my opinion alone, is something like the Windows and ARM laptop based around the Qualcomm 835 HP NVX2. Yes, it's EFI. Yes, it's ACPI, but it's not SBSA or SBBR compliant. In fact, you cannot boot an OS image which hasn't been tailored to run on the Snapdragon chip. All right. So in my view, that's basically EBBR. Now, allow me quickly check. I believe there's some chat messages just to make sure. Okay, got it. Okay, yes, roughly. Folks are chatting about the similar concepts. Okay, so what can we do about this, right? So we would like to bring standards to the edge. Great. Where should we start? Let's take the highest volume and cheapest platform that anybody can buy. I know everybody has their own favorite ARM SBC. Why not the Raspberry Pi? It's a $50 device. You can buy it anywhere in the world. There are no volume problems. In fact, even from just an image perspective, believe it or not, there are people out there who haven't heard about ARM, but they have heard about the Raspberry Pi. Also, the Pi presents a pretty solid ecosystem. It'll be around for a while. Right, so we are at Pi 4 today, and I can easily use the Pi 2. People laugh about Raspbian being 32-bit, but still, there's value in providing a common software ecosystem. The Raspberry Pi Foundation, actually, Raspberry Pi is an example of a successful vertically integrated ecosystem. But what I'll claim is that there's only so much space for a vertically integrated ecosystem. And I would say there's only space for one Apple, right? If you think you can be Apple, probably not, right? And there's also maybe not that much value. I mean, there's for a single vendor, they can extract some value of being able to provide this turnkey solution. But for others to be able to compete with that, we have to start doing something different, okay? So people claim there are boards out there that are Pi killers. Well, in what way though? A lot of them suffer from the same problem where they need a custom software stack. They're kind of a pain to reflash. I won't even know they'll have any system software that's mainline or upstream in 2 years that will run on them. All right, so that's the comment I'm making around, the Pi will be around for a long time. Some of these other boards may not actually be. I have a few bricks of my own that I can't do anything with. Okay, so Pi is cheap. I'll be around. There'll be a Pi 5. Maybe it'll be even better. Who knows? Also, is a Pi feasible? So for those of you familiar with a Raspberry Pi, they are pretty strange, right? So it's a system where the ARM cores take a backseat to the what's known as a video core or GPU. And yet the Pi 4 is a lot less strange than things have been in the past. So it finally has a regular interrupt controller. It finally uses USB 3 and actually uses pretty standard XHCI. So that's the regular USB 3 host controller. So is it feasible? Could you hypothetically claim it's standards compliant? It may be, right? I mean, yes, a USB 3 is wired up through PCI Express, but we could just pretend PCI Express doesn't exist. I mean, there's no physical slot, so it's not as if there's any meaningful value of exposing that. So maybe you could do level 2, level 3 as BSA compliance, right? Now okay, that's not great, okay? And here's where many folks might chime in and say, look, you can claim a toaster is compliant, right? But you lose 99% of its functionality, right? And so, okay, we're not trying to, kind of pass on a technicality. The real question is, what can be done today? But then, moving forward, can we use the Raspberry Pi 4 as a good example of as a good system, as a good example, where we can come up with that appendix for a common server, not server, but standardized systems and firmware specification that will actually give you, say, 80% or 90% of the functionality, or even 100% of the Raspberry Pi 4 functionality. I mean, we're clearly not there today, right? But we are where we are today, though, is that the Pi should be usable kind of as a BSA, as BBR, if you're willing just to use, USB storage and maybe onboard networking. I mean, that's not too bad, right? Okay. Anyway, so if we're going to do something, right, we should use a platform that's cheap and common. We should take a platform which is not obvious that it could be made server ready. So this way it actually poses some challenges and there's some discovery and work to be done to adapt specifications, because you can't expect every single edge system or a client system to start getting built like a server. That's never going to happen. So start with a system that is pretty far away from that. How else should this be done? It should be done out in the open community. It should be an open source project. It should be kind of a collaboration of equals. Again, this should be an example to others, right? You want to build a Raspberry Pi killer? Well, maybe you should focus on building something that isn't basically a dead end, right? In a sense that, hey, I'll be able to take upstream software, off-the-shelf Red Hat, Ubuntu, Debian, BSD, and put it on your board, and in 5 years it'll still be usable. Okay, so if you want to build a Raspberry Pi 4 killer, then this kind of a project on trying to standardize a Pi 4 will actually enable those. Okay, so maybe we're talking about edge and client, but for those of you who are server buffs, why would you care? So we know there's a problem today still, that there's not enough systems at a low enough price point for folks to start kind of kicking the tires with. So we think that a $50 device that kind of looks like an ARM server from a software perspective could be actually pretty interesting, right? I mean, $50 is $50, while $500 in low volume is exactly what it sounds like. And some of these other systems out there, unfortunately, are like way above $1,000. Okay. Finally, and this is my belief, is that many may share, is that there needs to be a good amount of client platforms to get that mass of developers. On one hand, if you look at ARM servers, they build upon the sort of the success that ARM had with the embedded mobile ecosystem, right? So, but there's this what I call a Grand Canyon between that world of the legacy world and this new server-ready world, and that doesn't exist for the other architectures, right? By the time anybody, for example, even thought you could build an kind of a production, or I'll say enterprise, it's a corny word, but enterprise-ready x86 server, x86 by then had already dominated basically small businesses and home computers. And at that point, it was obvious that the servers were just going to be a compatible extension of everything else. With ARM servers, that was very different. ARM servers are inherently incompatible. They were, standardized within themselves and may be compatible to the x86 servers to a degree. But now we got to go back and fix this other thing, right? Is what about hardware for the rest of us? What about all the non-server hardware that needs to feed into the ARM server ecosystem? And again, this will help do that. Okay, now what could you do with a standards compliant Raspberry Pi? Well, you could run SBBR and SBSA operating systems, right? Again, I'm choosing to define SBBR and SBSA here as standards compliant rather than server compliant. But even today, you could boot server compliant OSs, as long as you're okay with what you get. With that kind of firmware, should it exist, you should be still able to use EBR OSs, because device tree is I would say it's kind of the first class system description. On the Raspberry Pi 4, it's probably one of the only systems in the world that that's available even before any firmware boots. That's kind of cool. Okay, so are we doing something about it? Let's have a look. Next slide. Okay, so we have the Pi 4 task force today. And where does this project start? Way back in 2016, Microsoft actually created the first 32-bit EFI port of Tango Core. They put this up on GitHub. They did this as part of their 32-bit Windows IoT Core work. Also, later that year, Ard Bishuvel, I apologize if I just destroyed your last name, started the early work on 64-bit EFI for Pi 3 using Trusted Firmware A for PSCI, of course. And I thought I'd spend a few days kind of banging it all together, given that we have these I/O drivers on the Microsoft side and have this early port. And I kind of started from that, added USB support for Pi 3, which incidentally came, I believe, from some phone code that Linaro was working on. And then could boot Pi 3 SUSE on the Pi 3, 64-bit SUSE and Pi 3 with device tree. Some folks challenged to boot Windows on ARM. We got Windows on ARM booting. I work at VMware. I got challenged to boot ESXi ARM. I kept explaining to people how you couldn't do it, and I decided to actually prove myself wrong. So great. And the most important item here is February 2019, where a gentleman by the name of Pete Bartard kindly took my code from GitHub, cleaned it up, and started working with the TinyCore ADK2 platforms maintainers to upstream that. It was a massive amount of work, but what that means is today you can go and build TinyCore EFI firmware for your Raspberry Pi 3, 3B, 3B+, 3A as well, actually, and use it, right? And in September of that year, I started a joint collaboration project between VMware and ARM that basically became this community project to add Pi 4 support to the existing upstreamed Pi 3 EFI support. We showed this at the ARM TechCon. And it's been moving actually pretty fast, right? So another gentleman by the name of Jeremy Linton contributed PCI Express support for EFI, which meant we had USB 3 support in EFI as well. And then end of last year, we were doing SBBR boots of Debian and NetBSD. Even have onboard networking now, both working in NetBSD and Linux, and can even boot with a great set of limitations, Windows 10. And some of the recent wins there is we're getting the onboard networking driver cleaned up and ready for EFI. It was developed by the NetBSD ARM platform guy, Jared McNeil, and they'll be upstream soon. So most important place to track is rpi4-efi.dev. This is a blog. We track all the releases there, maybe some kind of opinion bits there, but that's where you can track exactly what works, what doesn't. There's a firmware status page, hardware status page. There's a GitHub page as well that contains releases and bug trackers. So the GitHub is where, again, we're actually working completely upstream now. Okay, so really the branching on GitHub is more internal private branches for people as they work on stuff. But we are fully working with EDK2 platforms upstream and with trusted firmware upstream as well. The bug trackers are kept though on PFTF, which can make sense. And we also publish the ACS compliance reports there. Here's an example of what the Server Ready blog is about. You can click on the About page that kind of gives you why it makes sense to make Edge standards compliant. And if people are interested about that, we can maybe cover that at the end of the session. And there's a status page as well. For every release, you can figure out basically what the bugs were fixed, what bugs exist, what works in the firmware, what works in the hardware, isn't being exposed to the operating system. So what does work, right? That's a good question. So trusted firmware, pretty much all set. Actually, PSCI CPU off was unimplemented, but that CPU off, not CPU on. CPU on was okay. CPU off, we're actually in the process of fixing that upstream. Support for serial ports, SDI, that's coming soon. That's the software delegated exception model for basically providing NMIs. Device support in the EFI itself. We have the RNG, serial ports. We support kind of fake NVRAM today, which is backed by a file. This is the code that's shared with the Pi 3. On the Pi 4, we may be able to squeeze some space on the SPI flash chip and use some space there for firmware variables, but that's to be done. We support EFI frame buffer using basically everything the Pi supports. So DSI, composite, HDMI, DPI. Basically, if you get the rainbow screen, it should work, including different kinds of virtual resolutions. We support the legacy USB 2 controller that's on Type C. On the Pi 4, of course, it's the regular Type A jacks on the Pi 3. We do support USB 3 in EFI. That's, of course, provided using the PCI Express based controller, the VLI chip. Support the RSON, that's the old SDHCI for micro SD. Pi 3 also had the SD host controller, which is not wired up to anything on the Pi 4. We now have the onboard networking driver, but of course, we all can also support USB NICs. Right, of course, PXE booting, iSCSI, RAM disks, HTTP boots, some are just upstream that. Lots of good stuff. Being able to do iSCSI booting your Pi, I think is pretty cool, actually. And PXE booting, regular kind of PXE booting. System descriptions, you can still boot device tree operating systems, and we support overlays. So if you describe some kind of overlay in config.txt, yep, that'll work. And we have very early ACPI support where we describe USB 3 and the onboard networking called GNet. There are quite a bit of challenges involved with supporting PCI Express, of course, on this board, and thus USB 3 because of silicon bugs. So there's a 3 gigabyte DMA limit. So for boards that have 4 gigs of RAM, what are you going to do? Finally, if you look at all the what I call the legacy devices, so these are all devices that are behind the GPU. So PCI and GNet are not. But say the MMC controllers, video framework for all this stuff actually has a 1 gigabyte DMA limit, and there's a translation there. Anyway, these challenges aren't things that necessarily violate standards, but have never been done before, have no meaningful support in any operating system. Yeah, that's a bit of a challenge. So how would we expose PCI Express USB using ACPI? So idea is that we'll just expose, so again, PCI is not standard on the Raspberry Pi 4. So you cannot expose it as ECAM, right? In fact, you also can't really expose it as almost ECAM. It violates the alignment requirements. You have to know that you can't scan before basically device 0, so that's not great. Also, PCI Express is not cache coherent. I am pretty sure somewhere in this BSA spec, it talks about coherency for PCI Express. Maybe I'm wrong here, but again, it's not really standard today. That's not really that's a challenge in itself. So we can just expose USB 3 as a straight up ACPI device. That is pretty easy, and all we have to do is just provide the node, right, in ACPI. Now, of course, EFI will it might shut off bus mastering on the way out, or an operating system on the way out of EFI might disable bus mastering for security reasons. So again, but this is easy. ACPI, unlike device tree, has this interpreted bytecode. Everything in the method, everything for the device is a method that can have side effects. In this case, we use the initialization method to go and make sure that the device is decoding and capable of doing DMA. Okay, so when the OS boots, it detects this ACPI device. Behind the scenes, the PCI device is enabled, and everything just kind of works. Great, right? So with that, actually, that gives you working Linux XHCI on 1 gig and 2 gig boards. Of course, it doesn't work on 4 gig boards. So why? Because of the DMA constraint. Now, the good news is that there is a way in ACPI to support this. There's this concept of a DMA method being described in a ACPI bus device, so which basically describes how child devices can do DMA. The constraints, it describes translation, describes limits. Today, again, the specs, the ARM specs never talked about it. And so it's been sort of spottily implemented by several OSs, but usually only in the context of PCI Express support. Okay, so first of all, of course, we added an option to just boot with 3 gigs of RAM, just to let people at least use 3 gigs of RAM on their Pi 4. So that's not ideal. But the good news is that it looks like there's like a 5-line patch for Linux to make USB 3 work with 4 gigs of RAM. And this is by basically honoring the DMA constraints, these underscore DMA method results for ACPI devices, which are not part of the PCI device stack. Also, in NetBSD, we have complete full support for this, which is pretty good. With Windows, Windows does not support this sort of DMA constraints today. So a lot of it's kind of TBD. And okay, so this way, so I guess you'll have to settle for these static pictures. Picture A is Technicore booting. Picture B is, of course, Technicore setup screen. And then you can see that, yes, PCI Express works in the EFI shell, and it's enumerating the USB host controller. The picture at the bottom, you see ESXi on ARM running in a Raspberry Pi 4 with 4 gigs of RAM. And the last picture is picture of Windows running the installer. And in this installer, you can't even do anything because, again, there's no I/O, no USB support. Another gentleman on Twitter managed to run Windows 10 on the Pi 4 using the USB 2, the DesignWare 2 USB 2 drivers, again using the Type-C port. And these are proprietary drivers from a company called MCCI. And actually, he only could boot with 1 gig of RAM because that specific driver doesn't anticipate seeing physical addresses beyond 1 gig. So yeah. Now, before we jump to the call to action, I'll mention that the Pi 4 code base is literally the same as the Pi 3 code base. All the work's done upstream. In fact, what I think is pretty exciting is that even if you don't care much about Pi 4 and ACPI, this EFI firmware that we have today. I think it's even a game changer for the Pi 3A, Pi 3B, for the compute module, which I hope to add support for soon as well. Because it already does fix some of the sort of deployment headaches you see around, say, the Raspberry Pi 3, how you have a non-standard way of network booting, describing these settings, even if you still have to use device tree for those. Okay, Summer, would you like to talk about the call to action?
Sure, thanks, Andre. So as wrapping up this session with the calls to action, first, if you would like to get involved, we are looking for more help. Of course, the project is open source, so if you go to the project link that was provided in one of the slides, you could see the issues, the discussions, the list of tasks that we have for the future. The actual patches are being submitted upstream to Tianocore EDK2, so you can also review those and test and participate and submit your own patches. Like you saw from Andrew's comments earlier, we had multiple folks jump in, developers, and help really move the project, move big obstacles from the project with their contributions. There is a chat channel on Discord dedicated for this project. So if you would like to join, it's the RPi for UEFI dev channel on the ARM developer ecosystem Discord server. The link for the invite is on our blog. You can directly email Andre and myself as well if you have questions or ideas. And the goal is really also beyond the Pi, right? The Pi is the first. It's the most important one in this towards getting to this goal of standardized OS and ecosystem support on these types of platforms. But other interesting platforms include the NVIDIA Tegra, Xavier, and other platforms. The Rock chip, RK3399, is popular with many platforms, both client and edge type devices. that are built around that SoC. In fact, Andre already has some port for that chip to UEFI, to EDK2 that needs more work and upstreaming. So that's on the list. And one other thing to add is, remember, SBBR is a standard. It's not about implementation. So Tiano Core and EDK2 happens to be the mature and popular and upstream implementation of UEFI, ACPI, SM BIOS. But you can have other implementations too, and there are U-boot UEFI implementations for EBBR that are focused on just getting the UEFI ABI working, maybe with device tree, but there could also be work to add ACPI support there. In fact, EBBR as a standard allows for either a device tree or ACPI, but you can even think of really having SBBR compliance implemented in U-boot if that's of interest to the community. And finally, from ARM points of view, we are really working on shaping the standards to make this type of enablement more possible, and using the Raspberry Pi project and these other potential projects as a way to learn more about this type of devices and drive changes in the standards if needed. So if you are interested in the standards work, we do have a consortium, a committee. It's called the ARM Server Advisory Council, or Server AC, because that's the ARM ecosystem committee where the server standardization, where SBBR and SBSA were defined. If you are interested in joining, you can send me a note, and we can talk about how you can participate in under that umbrella as well.
Yeah. So again, many of you may have some thoughts. You look at this, and like, well, it's a bit of a science experiment. So you got to use B3 working, and you have onboard networking working. That's great, but how will this ever work for kind of real edge platforms where you don't want to lose all the other interfaces? And how will this work for client platforms with power management? And so the ARM Standards Committee that Samara pointed out, there's this whole effort that's basically getting started right now, is specifically not about pretending that we can call everything server ready, but it's about scoping out both how systems being built today or effectively sold tomorrow, how those chips, how much of that can be usable in this more standards compliant manner. And I can go a bit into what I mean by that. But and also these long-term recommendations, right, to go and see how these systems could evolve in the future, how these chips. It's pretty obvious you can't just tell silicon vendors how they should go do things. It's always very easy to share an opinion, but in the end, they're paying for it, right? And today they're already paying to produce these chips. They're not going to randomly respin them. And so in many ways, it is about selling the silicon providers on the vision, on the idea that there is no reason why they should be all doing different things for booting, for example, or for discovering, or for PCI Express, or there are things that make no sense. And if we can slowly guide them to that and provide them an easy way of integrating something that works and that's cheap, so that everybody can standardize on. There's a large common base that can standardize on. But there are things that are present in the edge and the client footprints that are very different from servers. So for example, how do you standardize power management? How do you standardize, so like DVFS for devices? How do you standardize power on and reset blocks, or reset blocks? How do you standardize GPIO? And it seems like it should be, right? There's no reason why it shouldn't be. But then it's one thing to come up with a number of directives or prescriptions for what people should do. It's a wholly different manner to understand, well, can we come up with a mechanism to go and support these systems today, but support them in a way that doesn't involve platform-specific drivers in the operating system. So Drew Fustini asked a question in the Zoom chat, and if folks have questions, this is a great place to put them in. Like, how on earth could we support hat overlays? So I think one nice property of device tree is that everything that can be presented in device tree can be presented in ACPI. And this is not magic. This was done on purpose. There is this notion of device specific data device tree properties. Is basically a way to encode device tree properties within an ACPI AML device. Now, so that kind of means that if your device, so every device can be actually, every device tree device can be transformed into an equivalent AML object, okay? In fact, there's even a kind of a generic ACPI device that just means go look at the device tree compatible ID to figure out what it really is, okay? So you can already kind of convert, right, device tree to ACPI, you know, in principle, okay? And I know that some folks within ARM have been working on kind of creating those set of tools. Of course, when you start doing that, you want to be careful because you don't want to have different ways of describing the same thing. So there's already an ACPI way of describing something that should be adopted. And that actually makes conversion tedious because now it's not just a blind conversion, but you have to kind of know that, you know, not all objects are presented in this way. Some properties have to be translated in some ACPI way of doing things. Conceptually, if our EFI driver, if our EFI firmware today had an I2C driver, it could detect what the pi hat was. Right, it could basically grab that overlay right from there, from the hat itself, and turn that into an ACPI description, right? Or if you just use DT overlays and config that text, then again, the system is born with that device tree. EFI gets that device tree when it boots. You know, in my mind, again, this is a pipe dream. It'll be fantastic to see EFI configure itself based on that device tree, right? So today, pretty much every EFI implementation I've seen, they hard code what device, what addresses, what addresses they use. It'd be kind of cool if there was some concept of like an FDT bus Dixie, right? An FDT bus driver that would basically go and produce all the bus children that will be bound by the relevant EFI drivers. And again, since you have this description, you could, you know, the system is born with it. You should use that to generate ACPI. I mean, today we don't, but you know, my kind of a pipe dream vision is that you could have a single EFI binary that would boot on Pi 3 and Pi 4. And for those of you who know how different those are, you kind of see that there's some work to do towards that. But you know, I believe U-boot today supports configuration using device trees, so there's no reason why not. Anyway, so there is work to be done in figuring out what requirements client and edge systems have that differ from servers, and to make sure that those can be handled in a way without platform-specific drivers. In fact, even on servers, there's already an aspect there that is a little painful. For those of you who work on server-ready servers, you know that there's this concept of GPIO signaled ACPI system events. Again, that relies on a GPIO driver to be present in the OS. Okay, so yes, there's an ARM IP that people can use, but some silicon vendors do their own thing, right? And again, so now you have system events, which I would consider to be a pretty core notion. But now that's dependent on a platform driver. Okay, so that's kind of bad. But then, you know, why do we need a special driver for GPIO? Like, can't we abstract that somehow? So again, when you talk about abstraction, this is a pretty interesting topic by itself. For example, I had this notion that maybe we could just make PCC SCMI work, right? So by basically using the SCMI, and SCMI, I forget what it stands for, System Control Management Interface, maybe. It's basically a way by which operating system can basically, in an ACPI way, use shared memory to talk to the system control CPU, system control processor, right? But then again, like, what if that could be done in trusted firmware? Okay, Well, some vendors don't like the idea of putting more stuff in trusted firmware because it kind of ruins the perception of the kind of the root of trust, right? You don't want to have too much code there. Anyway, there's possibly many different approaches. Imagine if we got a Raspberry Pi Foundation people on board. There's no reason why the video core processor is implementing the mailbox the way it does today. What if it implemented SCMI, right? If the VPU was actually using SCMI command sets to communicate, then again, we could completely actually hide this without using even trusted firmware. There's questions about how or should, if we at all, abstract PCI Express access for edge SBCs. I mean, everybody gets PCI Express wrong, but when you look at SBCs, it's a special kind of hell because, yeah, it's not even close to ECAM. It's like random registers, and you write your bus to this and your device to that, and you use 32-bit only accesses, and then maybe it'll work. When you look at all of this, you're like, well, I'd love for people to adopt ECAM, but what if I have a fallback that's basically a trusted firmware interface for that? And there is a precedent. The Itanium did this with the system abstraction layer, SAL, and the Open Power ecosystem does this today with Opal. Opal is the firmware. But I mean, conceptually, Opal is more like EFI runtime services. It's not really a separate privilege like trusted firmware. So, and actually, if you're going to put random runtime interfaces, trusted firmware is one place, EFI runtime services is another. So all these options are up on the table. We'd love to see contributions in the space, because I think it's pretty clear we have to figure out how to make non-server systems become boring as well. And not just boring kind of in their own little world, but in a way where it keeps feeding the server systems as well. So it has to be compatible to some level. Do folks have any other questions that we can help answer? Okay, Samir, any parting thoughts?
I think that's good. If anyone have questions or would like to join, please follow up with us.
Yeah, the Discord. So the ARM developer ecosystem Discord server is a great place. How do you get to that? Go to the website rpi4efi.dev, and then there'll be a link there. That link is actually an invite, and so click on that, create an account, and then you'll have to manually navigate to the pound rpi4-efi-dev. Unfortunately, there's no easy way to create a link to a channel on a Discord server, but that's basically where all the development happens. So looking forward to seeing you there. All right, thanks everybody.
Thank you.
Thank you both. Have a good day.
Bye-bye.